Today, our topics are sources and Kirchhoff's laws. For our purposes in this course, circuits consist of their connections between two terminal linear passive devices and sources. Okay, so linear passive devices, by that we will see we mean one of three things: resistors, capacitors, and inductors. And in the first part of the course, we're just talking about resistors. For sources, well, we mean voltage and current sources. So we're going to talk about that today. But important thing here to begin with is this two-terminal idea. In this course, all devices are going to be two-terminal devices. So that would mean if we were to sketch them schematically, we'd see something that would look like this. So this represents some device and it has two terminals. Let's call the terminals A and B. Those are the places that we can connect wires to connect this device to some other device. For an electrical device, a two-terminal device, we need to specify two electrical quantities. First, the voltage drop, V, which is the voltage between terminals A and B, and the current. So we'll draw here the current, I. That's the current I that flows from terminal A to B through the device. Remember that voltage has units of joules per coulomb. It's energy per charge. So if this device had, let's say it's a 1.5 volt battery, and that means terminal A is the positive, terminal B is the negative. It would mean if I say it was a rechargeable battery and I took 1 coulomb of charge here at terminal A and pushed it through, well, it would come in with 1.5 joules more energy than it left the device. And so that would mean that it would have transferred 1.5 joules of energy to the device. Okay, so the device would be consuming that energy. And that process of the charge moving through the device, of course, is what we call current, coulombs per second. So the way we've drawn things here, these are really the reference directions for voltage drop and current, because current can flow in principle in either direction. It could flow from A to B or from B to A. But when we draw this arrow like this, it means that if current is positive, it flows in the direction of the arrow. So 1 amp, if I was 1 amp, it would mean 1 amp flows from A to B. If I was minus 1 amp, negative 1 amp, it would mean actually that the current flows in the opposite direction, flows from B to A. Likewise, this voltage drop, let's say it's 1.5 volts, that would mean that terminal A has a higher potential than terminal B. If this was minus 1.5 volts, it would be the opposite. Terminal B would have a higher potential than terminal A. Terminal A would have minus 1.5 volts more potential than B, which means it actually has less potential, right? A negative voltage above is the same as a positive voltage below. Okay, this set of reference directions where the direction of the current is the same as the direction of voltage drop, right? So both are from A to B, we call the passive sign convention. And why is that? Well, because remember that voltage times current has units of power. Because voltage is joules per coulomb, current is coulombs per second, the product is joules per second, or watts. So P is V times I is power. And what is the significance of this power, whether it's positive or negative? Well, if it's positive, think about what that would mean. So let's say we have 1 amp of current flowing from A to B, and there's a voltage drop of 1 volt from A to B. That would mean that each coulomb of charge which comes into terminal A leaves with 1 joule less energy. Well, where does that energy go? It goes into the device. The device consumes that energy. So in general, it consumes power. Now, what if P is negative? So for example, say the voltage drop is still 1 volt from A to B, but the current is minus 1 amp, meaning the current is actually flowing from B to A, flowing in the opposite direction. Well, then each coulomb of charge would come in here at the lower voltage and leave at the higher voltage, meaning it has higher potential energy. So it comes out with more energy than it went in. Well, where did it get that energy? It got it from the device. So in that case, the device produces power. Okay, so in the passive sign convention, this is the significance of the algebraic sign of P is equal to V times I. If it's positive, the device consumes power. If it's negative, then the device produces power. So, sources generally are the devices in our circuits that produce power, and then the linear passive devices are the ones that consume power. And certainly in the first part of the course, when we're just talking about resistors can only consume power. And so therefore, as we'll see, that power must come from somewhere, and it will come from the sources in our system. Now, for sources, these can be voltage sources or current sources. So a voltage source would be this two-terminal device such that V is equal to some fixed constant Vs. Or if it was a current source, then this current value would be fixed such that I is some constant Is. In other words, an example of this would be like a AA battery, which is nominally a 1.5 volt voltage source. So the positive terminal is 1.5 volts greater than the negative terminal. And so we're very familiar with things like batteries. And so voltage sources are pretty straightforward. Current sources are a little bit less common, but they're very common in integrated circuits and electronics and things. And so it's an important thing to understand. So we'll have voltage sources or current sources. Okay, so those will be our two types of sources. But we'll see also that sources can be either so-called independent sources or dependent sources. Okay, so we'll make that clear. All right, so our circuits are going to consist in connections between various two-terminal devices. Some will be sources and some will be these linear passive devices. And what we're going to need in order to analyze those circuits are some laws that tell us how voltages and currents combine when we connect these different devices. And so we'll have two laws. We'll have what we call Kirchhoff's current law, which talks about how currents combine and split up, and Kirchhoff's voltage law, which talks about how voltages combine and split up. Okay, so that's what we're talking about in this lecture. So let's now talk about an ideal independent voltage source. So here is the circuit symbol for that. So we got a circle here, two terminals, and we put a plus and minus inside the circle and give it a voltage label. She's red for that. So Vs. And of course this can also have a current flowing, and we'll call that Is. But because of this symbol, we know that it is a voltage source. That means that this Vs is fixed. And we say it's independent because this Vs is just a constant. It doesn't depend on anything else in the circuit. We'll talk about dependent sources a little bit later. Now, this is kind of a generic voltage source. Now, there's a special symbol that's used to denote a battery. It looks like this. But it is still, and this would be a plus and minus, it's still the same idea. It has some voltage, and then it can carry some current. Okay, so this would be for a battery. And this symbol, these represent the plates of like a lead acid battery, something like that. Okay, for our purposes, these are the same. It just means that the voltage at the positive terminal is Vs greater than at the negative terminal, and that's always the case. That's why it's ideal. Now, real batteries, you can load them enough that the voltage starts to change, right? They're not totally ideal, but in ideal ones, this voltage will always be the same. What will the current be? The current can be anything for the ideal case. It could be anything from positive to negative infinity amps. Of course, in the real world, you can't have arbitrarily large currents, but for ideal sources, yes. Okay. Now, it's important to keep in mind that you could have a voltage source in which this voltage is negative. Let's say it's minus 1.5 volts. What does that mean? Okay, so what is the significance of this voltage? It means that the voltage drop from the plus to the minus is minus 1.5 volts. Well, that means you're going down a negative amount. You're actually going up. So that would mean that this would be the same as a circuit where we swapped the plus and minus and then had the negative voltage. Okay, so this in this case, right, means that the plus is 1.5 volts higher than the negative. Okay, over here, so the right terminal, if we call it, let's call this A and B, and over here A and B. Okay, so A is 1.5 volts higher than B. What about over here? A is, B is the plus terminal here. So B is minus 1.5 volts higher than A. But that means that B is 1.5 volts lower than A. Same as over here, right? These are equivalent. So if I swap the plus and minus terminals and negate the voltage, I actually have the same source. It's just a different way to think about the same physical quantities. Let's see what we actually mean by that. So here we have two pictures of using a voltmeter to measure the voltage of a AA cell battery. So over here on the left, this is the positive terminal of the battery and the negative terminal. And the voltmeter has a red lead and a black lead. So the red lead is the reference positive terminal, and the black lead is the reference negative terminal. Okay, so we put the reference positive terminal on the positive terminal of the battery and the reference negative terminal, the black lead, on the negative terminal of the battery, and we measure 1.557 volts. That means that the red lead is higher in voltage than the black lead by 1.557 volts. All right, we're going from plus to minus. Okay, now over here on the right, all we did was swap the red and the black leads. So now this is our positive reference terminal, and this is our negative. If we were to get a positive voltage on this reading, it would mean that this terminal was higher in voltage than that. There would be a positive voltage drop from the bottom to the top. But we actually get a negative value. That means there's a negative voltage drop going from here to there. Okay, a negative voltage drop is a positive voltage increase. We're actually going up in voltage. Well, yeah, we're going from the negative terminal of the battery to the positive. But because we put our positive reference terminal of our measuring device down here and the negative terminal up there, we're going to get the opposite measurement, the negative measurement. Okay, so these are both physically telling us the same thing, that the voltage at the top of the battery is 1.557 volts higher than at the bottom, but we're measuring it in two different ways. Right? So we can always do this in the laboratory. And the same thing would be true, by the way, if we were to use this as a current meter. It'd be the same thing. If we swap the red and the black leads, we will get the negative measurement. That's describing the same physical system, but with a different reference direction for voltage drop. So here, voltage drop is positive going from top to bottom. And over here, voltage drop would be positive going from bottom to top. Okay, so that's what we mean when we draw two different voltage sources with different reference directions and to be the same physical component. They will then have opposite, in terms of the algebraic sign, source voltage. Okay, so now let's look at an independent current source. And so the symbol for this would be a circle, but with an arrow in it indicating the direction of the current. And we would have some, let's use our blue for current here. And then there would be some voltage drop. And if we use the passive sign convention, the voltage drop reference direction would be the same as the current reference direction. Okay. This is then a fixed constant. And the voltage can be anything. Again, for the ideal case. In the real world, there are limits on that. But for the ideal case, that voltage could be anything, but the current will be that fixed amount. So if that IS is 1 amp, it means 1 amp flows in the direction of the arrow, regardless of whatever else is going on in the circuit. Now, just like the voltage, a voltage source can have a positive or negative voltage value, and that really has to be interpreted in terms of the reference direction. The same thing is true for a current source. So I could have a current source, for example, here, say that had a minus 1 amp current flowing like so. And that would be equal to a current source where the current flows in the opposite direction and has the opposite algebraic sign, 1 amp, like that. So in other words, 1 amp flowing from right to left is the same as minus 1 amp flowing from left to right. You can flop your reference direction and then you add a negative sign to the value of your source. All right, so in this first part of the course, we're going to be talking about DC circuits. And that would mean that Vs is equal to a constant for a voltage source, or Is equal to a constant. Now later when we talk about transient circuits, these can be functions of time. Okay? So these are very general symbols, but for us right now in the first part of the course, these are just constants. This is a fixed current, and if it's a voltage source, it would be some fixed voltage. Now we come to dependent sources. So these are sources in which the voltage or current value of the source depends on something else in the circuit. Let me just give you an example of a circuit that would have this characteristic. Again, we haven't studied resistors yet, but these are resistor symbols. Here's some input voltage. And then here is a dependent source, which we represent by a diamond symbol. And with the plus and minus means it's a voltage source. But the voltage is now some constant, A sub V, times this input voltage over there. And then this is another resistor here called R out. And then this is an output voltage, V out. This is a simple model for an audio amplifier. So this is an input voltage, and then this is the amplifier part. It creates a much larger output voltage. This voltage here is controlled by the input, right? So a good audio amplifier, the output signal that goes to the speakers should be controlled by the input signal coming from the CD player or whatever it is. Okay, this would be an example of a voltage-controlled voltage source. This is a voltage source, and it's controlled by another voltage. So we actually have, there's four kinds for our purposes of dependent sources. We've got a voltage source or a current source. And these can be voltage controlled or current controlled. So they will all use the diamond symbol. So with the voltage sources, we'll have a plus and minus, and current sources will have an arrow. Okay, so these are voltage sources, these are current sources. So if it's voltage controlled, that means this value of this voltage would be something like, say, A, VC, where VC is the controlling voltage, and then that's the voltage that this source actually produces. Now, this could, in principle, be a more complicated function of some other voltages and currents, but for our purposes, we're just going to have things that are proportional, linearly proportional to some other voltage or current in the circuit. Over here, we could write this as, like, say, RIC. IC would be the controlling current, so this is a current-controlled voltage source. So a voltage is produced in response to some current elsewhere in the circuit. Here's a current source. We could say this is GVC. VC is the controlling voltage-controlled current source, and so the current is G times VC, and over here, maybe V times IC. This would be a current-controlled current source. So these are the four types of dependent sources for our purposes. Now, this looks maybe a little bit mysterious, but one of the places where this comes up a lot is in electronics, and we're not studying electronics primarily in this course. We will at the very end of the course just touch on electronics just very briefly, but I'll just point out that these kinds of models are applied to describe the behavior of transistors. And there are two main types of transistors. This is the so-called bipolar junction transistor, BJT. It's a three-terminal device. It has what's called a collector, a base, and an emitter. And our model for it, so-called small signal model for that, would look like the following. This is some little resistance, and we have a current flowing here, IB, and then this current over here is beta IB. So this is a current-controlled current source, and that models the bipolar junction transistor. And the other main type of transistor is called a field effect transistor. Generic symbol looks like this. This is called a FET. And it has three terminals: the drain, the gate, and the source. And the small signal model for it looks like this. And this was again from collector, base, and emitter. And this is drain, gate, and source. And this voltage right here is VGS, voltage between the gate and the source. And then this current over here is GM VGS. So this is a voltage-controlled current source, and that's the field effect transistor. So that's some examples of where these dependent sources appear, and that's why we're studying them. Now we consider Kirchhoff's current law, KCL. And this employs the idea of a closed surface. Okay, so here's a closed surface. In 2 dimensions, a closed surface would be a closed curve, right? That encloses some area. In 3 dimensions, it would be an actual surface enclosing some volume. And now, suppose we have some currents that are flowing, and they're all have a positive reference if they're flowing out. So they say this is I1, this is I2, here's I3, here's I4, and here's I5. Okay, so you got these 5 currents flowing out. And again, these are the reference directions. So if the current flows in the direction of the arrow, it's positive. If the current is negative, then it flows in the opposite direction from the arrow. So Kirchhoff's current law says that the sum of those currents is equal to 0. I1 plus I2 plus I3 plus I4 plus I5 is equal to 0, which we can say in words as the net current flowing through a closed surface is 0. Okay, so in this sense, electric current behaves like an incompressible fluid, like water. And so if you imagine that instead of these being the flow of current, these were the flow of water, say through pipes, well, the total amount of water flowing out through this surface at any time would have to be 0 because water is incompressible. So if water flows out somewhere, that same amount of water has to flow in somewhere else. So the net current flowing through the surface has to be 0. Now, you may prefer to, with your closed surface here, think about some currents as, say, flowing out. Maybe this is IA, and this over here is IC, and it's flowing out. Oops, IC. Let's do this here, IA, IC, and then maybe down here you've got ID. And then some other currents are flowing in, IB. And maybe this is over here is IE. Again, these are the reference directions. So if the currents are positive, they're flowing in the direction of the arrow. If they're negative, then they're flowing opposite. So you may want to have some currents be considered positive flowing out and others positive flowing in. And in this case, we would say the current flowing out equals the current flowing in. So mathematically, you'll see IA is out, IC is going out, and ID is going out, and that would be equal to the current flowing in, which would be IB plus IE. Okay, so that would be another way to express Kirchhoff's current law. It just gives you more flexibility in the kind of point of view you want to take. The most systematic way to do it is to have all the currents flowing out and then just say the sum of the currents is equal to 0. Meaning that if one of the currents is positive, then at least one of the other currents has to be negative to make up for that. So whatever flows out must flow in, or whatever flows in must flow out, because current and electric charge behaves as an incompressible fluid. Okay, so that's Kirchhoff's current law. Now, some results of that would be that if we had 2 devices, one after the other, like so. We say they're in series. And we draw a closed surface around both of them like this. Then we know that if there's a current I1 in the first device and there's a current I2 in the second device, well, I1 would be the current flowing in over here at the left, and I2 would be the current flowing out. So again, what flows in must flow out. So I2 would be equal to I1. So the two devices must necessarily carry the same current. You can also see that if you've made your surface this little circle there, all right, whatever goes in should be I1, must flow out, which would be I2. So that is Kirchhoff's current law. It says that electric charge, at least for our purposes, behaves like an incompressible fluid. Then we have Kirchhoff's voltage law, KVL. Okay, so how can we state this? Well, first of all, let's remember the idea of a voltage drop. If we've got a device like this, and we say, here's our reference direction for voltage drop, then in this case, right, the drop from top to bottom, if V is positive, the drop would be just equal to V. That's what that means. Now, so that, let's say this is terminal A, terminal B. So the drop going from A to B is V. And V could be negative, of course, meaning that it's a negative voltage drop. Okay, the increase going from A to B is what? Well, it's the negative of the drop. Okay, so it increases by minus V, right? And so if V is positive, minus V would be negative. It means it increases by a negative amount, meaning it actually drops by a positive amount. Okay, so that's the idea of a voltage drop and a voltage increase. And then KVL can be stated like this. Around a closed path, the sum of voltage drops is 0. Okay, so, for example, let's say we have this circuit here. There's a voltage source, and then there's some device right there, and then maybe there's another device over here, and a third device down there, and this is maybe a voltage source, voltage V1. Here's a drop V2, here's a drop V3, and here's a drop V4. Then KVL, Kirchhoff's voltage law, says, well, let's say we start here at point A, and we sum voltage drops going around clockwise until we get back to point A. That would be a closed path. So the first voltage drop, we're going from plus to minus, so it's a voltage drop of V2, and then we go from plus to minus, it's a voltage drop of V3, and then we go from plus to minus, so it's a voltage drop of V4, and here we're going from minus to plus, so it's a voltage drop of minus V1, because it's actually a voltage increase of V1, and that sum has to be equal to 0. And why does that make sense? Well, because a charge here at point A will have some voltage. And if I go around a closed path and I come back to A, I've got to have the same voltage. Okay, so therefore, the sum of all the changes in voltage must be 0, so that I end up with the same thing I started with. Now we could rearrange this, put V1 over by itself and say that's equal to V2 plus V3 plus V4. And in that form, well, the V1, that would be a voltage increase. So we could say, another way to say Kirchhoff's voltage law is that sum of the voltage increases equals sum of the voltage drops. And this would be around a closed path. And that's this form here. Okay, so this form, the first form was just that the sum of voltage drops would be equal to 0. And that's the most systematic way to approach it. But sometimes it's more convenient to think about, for example, voltage sources as being a voltage increase, and to do your bookkeeping this way. Okay, so as long as you keep the sign conventions and the actual signs correct, and you do the bookkeeping appropriately, you get the same results either way. Now let's denote another point in the circuit down here. Let's call that B. And here's another way to state KVL, Kirchhoff's voltage law. Voltage drop between 2 points is independent of path. What does that mean? It means that the voltage between A and B up here, if we took a voltmeter and we measured the voltage, right, so we'll say here's VAB, is that voltage between terminal A and terminal B. Well, that means that if I take this path through V2 and through V3, I sum those voltage drops, I should get VA. If I take this path through V1 and then V4, I should also get VA. So let's see, so VAB would be equal to, so if we go this way, we'd have V2 plus V3 would be the sum of the two voltage drops. So that'd be V2 plus V3. And if we go down this path kind of in the counterclockwise direction, we would have here, we're going from plus to minus, so it's plus V1. Here we're going from minus to plus, so it's actually a voltage increase, so that's a negative voltage drop. So V1 minus V4. And of course, if you look at that and look at these, they're equivalent. If I just put the minus V4 over here as a plus V4, I get this equation. And then if I subtracted the V1, I would get that equation. Okay, so that's another way to express Kirchhoff's voltage law. In this class, we generally make what we'll call the perfect wire assumption. And that is that if we have a piece of wire, no matter how long it is, that's carrying some current I, there is no voltage drop between the two ends of that wire. And as we'll see in a future lecture, that means that we assume the wire has no electrical resistance. So that's not rigorously true. Of course, real wires, at least at room temperature, or if they carry a current, are always going to have a little bit of a voltage drop. They have a little bit of resistance. But we'll see in the future lecture that if the wire is of sufficient size and made out of a good conductor, that resistance is generally going to be negligible compared to any other resistances in the circuit. And that means that if we imagine, say, we have some voltage source here, and then we got some long wires, and at the end of those wires we have some device, then maybe this is a voltage V1 in this source, and this device has a voltage drop V2, and we have a current, say I, that's flowing like this, kind of in a clockwise orientation. And we might imagine in reality there will be some voltage drop between the ends of the wires, but we're going to assume that those are effectively zero. Okay. And in practice, they're negligible. All right, they're so much smaller than the voltages related to the actual discrete devices that we can neglect it. Okay. Now, if you have a really long wire and it carries a lot of current, then that voltage drop may not be completely negligible. And then you have to give it some thought. Okay, so we'll talk about this again in a future lecture. Now, with Kirchhoff's current laws, we have to consider the possibility that a circuit may have valid or invalid connections. So we have to talk about what are valid circuit connections. So valid circuit connections do not violate KCL or KVL, the voltage and current laws. And if they don't violate those, then we've got valid connections. So let's look at this with respect to sources. Suppose we have two voltage sources, like so. Connected side by side like this. We see they're in parallel. And suppose we have this first one, it has a 12 volt source, and the other one is also a 12 volt source. Is this a valid connection? Okay, and so let's imagine, right, there's a current I1 that flows into this source and a current I2 that flows into that source. Well, let's see. Let's talk about Kirchhoff voltage law. If this is A and this is B, the voltage law requires that the voltage drop from A to B be the same regardless of which path we take. So this, going this way, it's a 12 volt drop. Going this way, it's a 12 volt drop. Or equivalently, we could say if we start at A and go all the way around, we get a 12 volt drop and then a negative 12 volt drop. We get a 12 volt increase. Okay, so yeah, KVL is satisfied here. And as far as the currents, well, there are no constraints on the current in an ideal voltage source. So these currents could be whatever they need to be. Right? And then maybe there's an I3, up here. So there's no constraint on the current. So this is valid. This is a valid connection. What if, on the other hand, we had these two voltage sources? Oops. And let's say this was 12 volts and this was 6 volts. Okay, we have some currents, I1 and I2 and so on. Is this valid? Well, no. Because KVL then, if we look at this, if we go from A to B through the 12 volt source, we have a 12 volt drop. If we go through the 6 volt source, we have a 6 volt drop. That violates KVL. You can't have this. You can't have the voltage between A and B be 12 volts in one path and 6 volts in the other. What would actually happen if you put a 12 volt battery in parallel like this with a 6-volt battery, massive amounts of current would flow out of the 12-volt battery and into the 6-volt battery, probably so much that the batteries would quickly heat up and crack or maybe even explode, catch on fire. It would be a bad deal. Okay, and what would happen? So much current would flow out of this 12-volt battery and so much into the 6-volt battery that these two voltage drops would equalize and become the same. Okay. But if they were, that's if they're real batteries or voltage sources. If they're ideal, you would get infinite current flowing, which, of course, can't happen in the real world. So this would be invalid. And generally, an invalid connection in a circuit, if you did that in a real circuit, something's going to burn up or a fuse is going to blow or something like that. So we see that we can put equal voltage sources in parallel. And we actually do this all the time with batteries. We put a number of, say, 1.5 volt batteries in parallel so we can get more current. But you can't put unequal batteries in parallel. What about let's look at an extreme case of this. What about a 12-volt battery in parallel with a 0-volt battery? Well, a 0-volt battery, that's just a wire. That's just a short circuit. So what if we had this situation? This is 12 volts. Okay, so now from A to B going this way, you'd have 12-volt drop, and this way you'd have 0-volt drop. What would happen? Of course, if I short circuit a battery, massive amounts of current is going to flow, and that battery is going to quickly fail. Something bad's going to happen. If you did this in a household circuit, of course, you'd trip a circuit breaker. Okay, so this is certainly invalid. Don't short circuit a voltage source. Okay, so identical voltage sources can be put in parallel, but non-identical voltage sources cannot. Now, what about sources in what we call series, end-to-end like this? So let's say we've got here a voltage source and here another one. And let's say this one is 12 volts and this one is 6 volts. And let's see, we've got a current I that flows through both of them by KCL. The same current has to flow through both. Whatever comes in goes out. Is there a problem with this? No. The current through a voltage source is unconstrained. So these can easily both have the same current I. And they're not in parallel, so we don't get this problem that we talked about before. And what happens here is simply that, in this case, if we look at the voltage between the rightmost point and the leftmost point, we would have a voltage increase going from left to right of 12 plus 6 is 18 volts. And this is another thing we do all the time. We take, say, like AA batteries, and we put them one after the other in series like this, and their voltages add. So we can get, if they're both 1.5 volts, and we put two in series, we get 3 volts. And if we put 4, we get 6 volts, and so on. So we can put any voltage sources in series like this, one after another, no problem, regardless of their voltage values. If we put them in parallel, they have to have the same voltage value. Otherwise, it's invalid. So this is certainly valid also. Now let's look at current sources. Let's put current sources in parallel. Let's say this is point A, and this is point B. And here are our two current sources. And maybe the first one is 1 amp, and the other one is the 2 amp current source. And there will be some voltage V here between terminals A and B. Is this a problem? Well, let's see. The voltage drop across a current source is unconstrained. It can be anything it needs to be. So it's perfectly okay for these two to have the same voltage drop. Let's see. So we have 1 amp of current here and 2 amps there, and they flow into this. We put a little circle around here as our little closed surface. So we know that 1 plus 2 is equal to 3 amps would have to flow out. And that's as long as we allow that 3 amps to flow out, there's no problem. And of course, that would mean also 3 amps would flow in here. Okay, so this is valid. We can put arbitrary current sources in parallel like this, and their currents will add together, and they'll all have the same voltage, no problem. What if we put them in series? So say this is our 1 amp and this is 2 amps. Okay, well, we can see that's going to be a problem. Because if we put this inside a closed surface, what do we have going on? We've got 1 amp flowing in, but 2 amps flowing out, and whatever flows in flows out. So that is a problem. This is invalid. Right, by KCL. Up here, we had a circuit that was invalid by KVL, violated KVL. Okay, so for current sources, to put current sources in series, they would have to have the same current value. Right? If they're both 1 amp, then this wouldn't be an issue. But we can put arbitrary current sources in parallel, as many as we want. For voltage sources, we can only put them in parallel if they have the same voltage value. But if they're in series, we can have an arbitrary number of voltage sources with any voltages, and we can put those in series. Okay, so those are, with respect to sources, those are considerations for valid and invalid connections.